Is it okay? Okay. So I will use x capital A and capital B to denote the angular variable, and this induced metric will be denoted by g slash dxa dxb. So what I've seen in Henry's talk, the Penrose diagram of Schwarzschild space-time. We have the future event horizon and future non-infinity. And this coordinate system is actually not regular along the event horizon, on which it's convenient to work with this coordinate system. V is t minus r plus 2m log r minus 2m over m. And let me use rho. This is, as a function, is the same as r, but to distinguish different coordinate vectors, let me denote it by rho. Then the metric takes the form minus 1 minus 2m over r, which is rho, dv squared, plus twice d rho, dv, plus, well, the spherical part doesn't change at all. So this is pretty similar to the bounded stack coordinate we have seen these days, but it is the incoming direction. So here is plus 2 d rho dv. In particular, this is a regular coordinate all the way up to the horizon. And if we compare the coordinate vectors, dd rho, that's, sorry, let me start from v, ddv is dd, the same as ddt. It's still a Killing vector field, so denote it by capital T. And what is dd rho? That is minus 1 minus 2m over r minus 1 ddt plus ddr. And let me denote this by L lower bar. It is the incoming. Yeah, t minus r, retarded, advanced. Yes, yes, right. Yeah, you're correct. T minus r is u. Yes, thank you very much. I want t plus r. So ddv is the same as capital T, and dd rho, you start with ddr, and you need to put some multiple of dt, and this is the coefficient. This is the null vector, that's the incoming one, L lower bar. And let me define the outgoing one, ddt plus 1 minus 2m over r ddr, that's L. There are null vectors, L equals L bar, 0, and L dot with L lower bar equals minus 2. And let me define my regular vector fields D to be L lower bar, and I want 1 over r theta, and 1 over r over sine theta d phi. And I will also denote this part by gradient slash. And this notation is consistent with this one. This is, well, d theta over r squared plus d phi over r over sine theta squared, and sum over them. Just, well, in the logarithm manifold, there's no natural way to define what's the L1 norm, so one need to specify a frame, and this is the frame we are going to use. Okay, so the next step is to generalize this approach to the Schwarzschild space-time. The first thing one need to take care is, well, this t is not always time-like. T dot t, that's minus 1 minus 2m of r. It equals 0 at the event horizon. So yeah, we're still going to study the wave equation, box G equals 0. Because T is still killing, we still have the divergence theorem, the divergence of TAB, TA, it is still 0. Therefore, we can apply the divergence theorem to the generalization of that slice. The slice we are going to take, it looks like this. We still fix a large radius R0. After R0, we want the slice to be null. Before it, we want it to be space-like. Furthermore, we want it to intersect with the event horizon transversally. The reason we don't want to go to here, this is the bifurcation sphere, is, well, T is now along the horizon, which is not good, but at the bifurcation sphere, this vector is actually 0. So it's even worse. Which one? T, the killing vector field. It's at the event horizon. Well, along the event horizon it is now, but at the bifurcation sphere it is 0, a 0 vector. And we still denote this region by the tau 1, tau 2. This is sigma, tau 2. Okay, now let's apply the divergence theorem in that region. All we have is integration along sigma tau 2, TAB, TA, and B, the volume form induced by N, plus the event horizon part, H plus tau 1, tau 2, TAB, TA, and H plus B, the volume form induced by this normal vector, plus the contribution from the non-infinity, I plus tau 1, tau 2, TA, is equals the initial energy. T, TAB, TB, and A. Okay, this is an equality, and the integration along the non-infinity is understood as taking the limit. One take the null slices, and for each null slice, you have some equality, and you take the limit. This is understood in that context. So we have the contribution along the event horizon and along non-infinity, but for most of the time, we are going just to throw them away. They will give us some positive term and change this equality to an inequality. So this is not a conservation of energy, but the energy would at least be bounded by the initial value. So now let's take a closer look about what is this integrand near the event horizon, because that's the place where T becomes a null vector. To do that, it's still convenient to do the null decomposition. So T, that's half L plus 1 minus 2m over R, L lower bar. And what about the normal vector? Well, it's a time-light unique vector, so we can always write it as some coefficient alpha times L plus beta times L lower bar, where alpha is a function of R as well as beta. And they will be positive. Therefore, TAB, TB, and A for the LL part, we have alpha over 2 gradient L u squared. For the L bar part, we have beta over 2, 1 minus 2m of r gradient L bar u squared. Finally, from the cross term, we have alpha over 2, 1 minus 2m of r plus beta over 2 times the angular gradient. Alpha and beta are positive. However, the derivative of u along the incoming direction still degenerate on the event horizon r equals 2m. In other words, this energy is not equivalent to sigma tau. Even if we restrict on the space-like part, it's not. It does not control this direction. So to deal with this problem, Darfomos and Wronski, they discovered the so-called redshift vector. Yes.
So your integral, is it future? You have the minus side?
No, it's not future. It's past. Oh, thank you. I forgot a minus sign over here. Yes, L and L bar are future vectors. So L bar. The picture is correct. The formula is wrong. Okay. So they discovered the so-called redshift vector Y, which is a vector field satisfy the following condition. Let me fix a radius r plus between 2m and 3m. We will see in a minute why r plus need to be less than 3m. And a constant, a positive constant, to be determined later, sigma. And I want this to satisfy the following 5 conditions. First, the lead derivative along T and the lead derivative along the angular Killing vector fields of Y is 0. In other words, that the vector field depends only on the R variable. Second, for R larger or equal to R plus, Y is identical to 0. Third, Y is time-like in 2m to R plus. In other words, Y dot Y need to be negative. Fourth, along the event horizon, this is minus. This is L lower bar. Finally, the gradient along the L lower bar direction of Y on the event horizon need to be minus sigma L plus L bar. Okay, so these are the 5 conditions Y need to satisfy. And let's see why do we need them. From the 3rd and 4th condition, 3 and 4, implies that for any epsilon greater than 0, if we add the slight amount of y into t, TAB, instead of contract with just t, we put t plus epsilon y. A and B, B and A. Well, this time, this is bounded below by epsilon times du squared. And it's always bounded by du squared. Because the degeneracy occurs along the event horizon. And, well, we add a direction which is exactly the exactly the degenerate direction. So one would like to consider the current Jy to be TAB, YB, and apply the divergence theory. And this condition tells us it has a good boundary term, but what about the bulk term? So let's compute the divergence of Jy and the event horizon. So to do that, we need to compute the symmetric gradient of y. Let's still do the now decomposition. It can be decomposed into C L bar, L bar, L bar, L bar part, plus C L L, L L part, plus C L L lower bar, 1L, 1L lower bar, plus CLA, L and DDXA, plus CL bar, A, L lower bar, A, DDXA, and finally the spherical part, CAB, DDXA, DDXB, A, B. Okay, from the first condition, it is doesn't depend on T and R. These two would vanish. That would correspond to a spherical symmetric vector, which doesn't exist unless that's a zero vector. Also, this part would be proportional to G upper to the spherical, to the round metric. Therefore, the contribution of this part is a certain constant times gradient L U times gradient lower bar U. And the contribution of the remaining three parts is very easy to compute. Here we have gradient L lower bar U squared. That's gradient L. And here is the angular part. So one would like to make the coefficients, these three C's, to be positive. And that's the reason to make the fifth requirement. For example, so these two, this will be proportional to sigma. Let me compute CLL. CLL, that's a quarter of gradient L lower bar y dot with L lower bar. Just contract this with L lower bar and L lower bar, which by our assumption is a quarter minus sigma L plus L lower bar, L lower bar. L dot with L lower bar is minus 2, another minus sign, so it becomes sigma over 2. And one can do a similar computation for CL and CL L lower bar. However, this one cannot make it arbitrary. Here we can just choose sigma to be large to make these two parts arbitrarily large. But for this one, that's required. It depends on the positivity of surface gravity. I probably want to keep this sigma tau. Okay. So what is that coefficient? See L lower bar, that's a quarter gradient of L in the L direction, L, Y, in the product with L. Pull out the derivative and move it to the other side. That's minus a quarter. Y along the horizon, that's L lower bar, gradient L, L. And L is along the horizon is actually a Killing vector. That's the same as capital T. It's a null Killing vector, so it's the gradient along itself is proportional to itself, kappa, for some constant kappa. And this is the surface gravity we have seen in Henry's talk. So L.
Well, my question is that, well, suppose you have a general static space-time.
Yes.
And the ddt become null at the zero static potential.
Mm-hmm.
I mean, does everything carry over, and you can still construct this kind of Rorschach vector?
If that's a static space-time, but
Well, I guess you still have the surface gravity.
yeah, I mean here we can see for these two, well one can just make them as large as one wants, but for this one requires the surface gravity to be positive. So
That's it.
yes, that's
So
the
if you have static space-time, you have, but that would be in terms of the Hessian of the static potential.
mm-hmm. Yes.
The surface gravity
Mm-hmm.
corresponds to the
Hessian,
Hessian.
right.
So if you actually
Gradients.
the gradient square. The static potential is defining equation for the horizon. The gradient square.
But I need to think a little bit more because
Still the surface gravity.
because in the static, if you think it as a static manifold, then then you're at the bifurcating sphere.
Yeah.
If I just literally compute everything here, this will be zero. This will actually be zero. So I need to think more think about how to go to the future event horizon instead of the bifurcating sphere.
You don't use the Einstein equation. You just need, right? I mean, you just need a surface gravity to have a sign.
Yeah, just
along the horizon.
yes, that's right. The surface gravity need to have a sign, but I need to think how we cannot compute everything on the bifurcating sphere. Otherwise, this is a zero vector, and so this will be zero. And but only thing it requires is positivity of surface gravity. Surface gravity is this constant. And this is kappa over 2. In Schwarzschild, kappa is 1 over capital M. The only thing we want is its positivity. So what do we have? So we can simply choose the sigma to be large. We have some cross term over here, but it's not important as long as sigma is large enough. Therefore, the divergence has a sign at the event horizon. Therefore, by continuity argument, there exists a radius r minus between 2m and r plus, such that between 2m and r minus, the divergence of jy is bounded below by du squared. And just by looking at the form of gradient jy from 2m to r plus, jy, this is always bounded by du squared. From r minus to r plus, we don't have a good sign, but it is always bounded by du squared. And this is the redshift vector. Okay, any question? So by using the redshift vector, we have non-degenerate boundary term. Now let's look at the Morowitz estimate. It's actually quite subtle. Oh, the existence? So one, so well, one look at the definitions, and well, one can just choose y to be some alpha of r L over bar plus beta of r times L, and one will have some open condition on the behavior alpha as well as its derivative. Then right, then it's not hard to show that for any sigma one can construct such redshift vector. Okay, for the redshift, so for the Morowitz estimate, let me tell you the what we're going to have at the end. There exists a current JMA such that the divergence JMA is bounded from below by 1 over r cubed, 1 minus 3m over r squared dt u squared plus 1 over r cubed dru squared plus 1 over r, 1 minus 3m over r squared gradient slash u squared plus 1 over r cubed. The main difference from the Minkowski's case is this factor, 1 minus 3m over r squared. And it needs to be there. The reason is there exists a trapped non-geodesic in the Schwarzschild space-time. One can actually write it down explicitly. Gamma s, if that's t equals s, r equals 3m, theta equals pi over 2, and phi equals 1 over 3 root 3m times s. This is a non-geodesic. So here, let me say this is the black hole. What it does is, well, it rotates along the black hole, but the radius doesn't change at all.
What do you mean by this? You mean the
So,
coordinates are given by this?
yes, this is our t, r, theta, and phi coordinate. T, r, theta, phi. So it's at the equator. And by the geometric optics, one can actually construct a solution of wave equation along the now geodesic. And let me give you a sketch of it. That's called the Gaussian beam solutions. So let W, y1, y2, y3 be a coordinate system near the null geodesic. W is a null coordinate in the sense that dW dot with dW equals 0, and W equals 0 is exactly. And Yes, and this is dw dot dw equals 0. And let me see. And consider the, let me think a little bit. W needs to be a null coordinate. Okay. Now let lambda to be a positive number. Consider u lambda to be, yes, here I want gradient W to move along this trapped null geodesic. And u lambda is defined to be a lambda W y times e to the I lambda W. So what is its box? Box u lambda. Let's just expand everything in terms of the order of lambda. So the highest order, that would be I lambda squared, gradient W dot gradient W, which is 0 by the assumption. And the next order, we have I lambda times.
What do you mean by order?
So here we have lambda squared, and here we have lambda. In terms of power of lambda. And we have box W plus twice gradient A lambda dot gradient W e to the I lambda W. And the last term, box A lambda times e to the I lambda W. So the first term is 0. It goes away. So to have an approximate solution, this is higher order, this is lower order in terms of power of lambda. So one simply assign the initial value of A lambda and solve the ODE twice gradient A lambda dot gradient W plus box W equals 0 to make this goes away. Roughly, it gives you an approximate solution of wave equation. Then if you want to get an exact solution, one can use this as a source term and solve it. And by using this, one can choose A lambda to concentrate along a very tiny neighborhood of the null geodesic. And at the end, you will get the solution will be concentrated along the null geodesic. As you make lambda larger and larger, depending on how much you want it to be concentrated along gamma. Okay, so why is it a trouble for the Morowitz estimate? Well, here this is kind of heuristic. For example, how long can you get this null coordinate along the null geodesic? But to tweak it a little bit, one can make it quite rigorous. Everything is smooth.
Yeah, but I mean, like, do you have any LP control?
So everything is smooth, and the initial EB norm is bounded. So it has, well, every estimate we had before. So, let's call it Minkowski. The Morowitz estimate tells us integration from tau 1 to tau 2, integration along the R3, 1 over R squared, du squared, dx, dt. I'm throwing a lot of other terms, but this is still bounded by the initial H1 energy. Yeah, the initial H1 energy. But this kind of estimate cannot be true. Not true. In Schwarzschild. Just because, well, we have the conservation, well, of the EB energy. The solution is concentrated along this null geodesic. So, well, the weight in the other direction doesn't matter.
When you take a
delta function. So it's L2 norm. Well, sorry. H1 norm will be bounded, but its higher derivative will blow up. Yeah, its higher derivative will blow up. Yes. So the so lower frequency you don't have the you can actually have the Moore estimate as before. If you recruit yourself at a low frequency, then one actually do have this. But so the trap phenomenon only occur at a high frequency, corresponds to lambda, goes to infinity. And the reason is for that kind of lambda solution, U lambda solution, this is actually about integration from tau 1 to tau 2 EB of U lambda dt, which has the conservation tau 2 minus tau 1. So which is a contradiction. And that's the reason why we need to put in any estimate, any space-time integrated estimate you have, you need to put this degenerate factor. Okay, except that the Moore estimate is pretty similar as in the Minkowski case. And finally, the RP part is actually the same. J from P, same as. Therefore, we define the final current, Jp. We need Moore width. We need the T current. And now we need the redshift current to remove the degeneracy along the horizon. And we still have the RP current. The epsilon y here is chosen to be small such that the error term in this region can be absorbed by the Moore width. The Moore width degenerate on the Flournoy sphere, but away from the Flournoy sphere, it's coercive. Then one still have these three things, except that the boundary term is still E bar P, the divergence is still non-negative. However, the divergence for P from 1 to 2 is not EP minus 1 because of, well, that degeneracy. EP minus 1 dg. But one can remove that degeneracy by commute with T and angular Killing vector fields. Here we have ddt. This is the angular direction. EP degenerate of Tu omega u is bounds the non-degenerate P energy. Therefore, the conclusion still holds, except that one need to change the right-hand side. That's not just the E2 energy of U, but one need to commute with those scaling vectors, and one need to commute it twice because we use bootstrap. We use bootstrap argument twice. To 2 U times 0, where K is the vector field T omega 1, omega 2, and omega 3. And this is the decay of wave equation in the Schwarzschild space-time. Okay, any question? Yeah, so sorry for my sloppiness. It means the EP degenerate energy of Tu plus the one for omega u. Yeah, so u plus, to be more precise, omega 1, omega 2, and omega 3. So the next natural question is what happens in the Kerr spacetime. For angular momentum small, you can treat Kerr as a perturbation of Schwarzschild. Almost everything works out by a perturbative argument, except the Morowitz estimate. The reason is exactly you have some degeneracy. If you perturb it away, you need to be very careful about that term. So there are two ways to resolve this issue. One is done by Davos and Rodnyansky. And they use the Fourier transform in the Kerr spacetime. The trap now geodesic depends, well, actually on the frequency. That's not always. Absolute value of A. That's the angular parameter of the Kerr spacetime. This is G A Kerr metric. I can't, and I will not write down the explicit form of it. Let me just say Gm A. That's Gm plus big O A over R squared. That's a perturbation. We can treat it as a perturbation of the Schwarzschild metric. But the difficulty is there is still trapped now geodesic, but it's not always at R equals 3n. It depends on which frequency you are at. So Davos and Rodnyansky, they use the Fourier transform to so here A times symmetric 2 times A is a scalar. They use Fourier transform to really localize, look at which now geodesic is trapped. And there's another proof by Anderson Blue. Anderson. And they use the Carter tensor, the Fourier. Carter tensor. It's related to the conformal-Killing Yano tensor. It's a hidden symmetry of the Kerr spacetime. Essentially, what they did was they reformulated the Morowitz estimate by using the Carter tensor in a way that's stable under these A perturbation. So they can just perturb it away and everything goes through. And there's a lot of other works for what happens for A is large and for the extreme case, but let me stop here. Okay, so this is the linear wave equations in Schwarzschild and some in Schwarzschild space-time. Now I would like to talk about semi-linear equations. And also for simplicity, let me restrict myself just in the Minkowski space-time. Semi-linear. So let me first state the local existence result. Let f u du, that's a smooth function in R cross R4. Let S to be a integer greater or equal to 6. Then for any initial value f and initial value velocity g in h s plus 1, let me remind you that's hs norm in R3. R3, there exists a time t depending on f, g, and this function f, such that the system star, that's box u equals f u du. U initially is f, and its time derivative is g. As there exists unique solution u in C2 0 to t equals R3. I will not go into the detail of the proof, but I will tell you the main ingredient of it. Strategy is by iteration. Define u minus 1 to be identical to 0. Solve um by box um equals f minus 1 d minus 1. And here one need to first assume these are smooth functions. With complex support later, one can remove this assumption by approximation. Then, by its iteration, um is smooth everywhere. And one tried to argue that by taking t to be very tiny, you actually converge in a suitable banana space. And there are two ingredients in doing that. Yeah, so thank you. The initial condition is f and g, um x. In proving it's actually a Cauchy sequence in suitable banana space, there are two ingredients. One is energy estimate we have seen yesterday. Energy estimate. That is summation alpha less equal to 1. The alpha u, its L2 norm, time t, is bounded by a constant times summation alpha less equal to 1. The alpha u, L2 norm at time 0, plus integration 0 to t, L2 norm of box u, t prom, dt prom. And this holds for any smooth function. You don't need, well, we have box u over here. The other is pointwise estimate. That is simply the Sobolev inequality. The L infinity norm of u along R3 is controlled by its H2 norm. 2 times 2, that's 4, greater or equal to Kp is greater than the dimension 2 plus 2 equal larger than 3. It's R3. Okay, so this is the local existence. So what about the global existence? Whether the solution exists globally, at least for small data. So let Q du be a quadratic expression. I will be more specific about what is Q in a moment. So the question is, let's say f and g, they are smooth function with convex support. And one look at the system, box U equals Q du, U0x equals epsilon times f, dtu 0x equals epsilon times g. And one asks whether can one assign epsilon to be very small, such that the solution does not only exist for a finite time, but has long time existence. When does U exist in well, actually, in higher dimensions, under reasonable assumption of Q, this will be always true, but it is quite subtle in the 3+1 dimension. Fritz John, in 81, he gave an example that if Q du, that's dt u squared, then every solution, then for any f and g, u blows up infinite time. So no matter f and g, of course, this is not trivial, of course. As long as the initial condition is not trivial, the solution will blow up in finite time. So one need to impose the null condition on the quadratic term that was discovered by Kleinman and Christodoulou. Okay, to explain what's the null condition, let me define this collection of vectors. D is L, the outgoing null direction, and the angular derivative. D, that's D bar. D is L lower bar, L, and angular 1. Degenerate the 4-dimensional tangent space. D bar lose one direction, that's the incoming one. Q, and let me use the Killing vectors. We have time lag 1, rotation 1.
Still the same notation. Both are future.
Yes, both are future. Yeah, yes, both are future null vectors. One is outgoing, one is incoming. T omega, and I also want to use the space-like translation. D1, D2, and D3. Okay, so assumption. Is Q du can be written as summation x in d bar, y in d, a smooth function fxy, x times dxu times dyu, where this fxy is a smooth function. And if we take a derivative along the Killing vectors multiple times,
So 1, 2, 3
are xyz, yes, xyz. And take the LV norm. See, we want it to be bounded. And let me give you a simple example. Q du, one can just take it to be eta AB. We are in the Minkowski space-time. dAu, dBu. That's in terms of the null vectors. That's minus gradient Lu, gradient L lower bar U plus. The reason is for the wave equation, the derivative along the outgoing null vector and the angular direction actually behaves better than the general derivative. The L bar derivative behaves worse. And this condition says that,
What's condition on alpha? You have K alpha.
so alpha is the multi-index. Alpha S, multi-index. So here I have 1, 3, and alpha j, 6, 7.
So that means for any
Come.
for any alpha.
Yes, for any alpha, for any multi-index.
C alpha.
Yes, yeah, exceed C alpha xy, such that it is bounded. For the easiest example, actually the first one proved by Christodoulou and Kleinman, was this one. One just take the gradient u dot with gradient u. That's L is a good direction. It's contracted with a bad direction. That's okay. The angular directions are good. So, and in this case, C, well, this F is simply 1. Well, the thing for example, in the wave map into the hyperbolic space, it will satisfy this kind of null condition. Or in certain gauge in a harmonic gauge, the harmonic map gauge, the linearized Einstein equation satisfies not this one, but a weaker version of this null condition.
When you check the DTU squared, it's not satisfied condition.
So DTU squared, let's decompose it into the null directions. dt is a half L plus L lower bar, so dt u squared, that's a quarter. The Lu squared plus a quarter. The L lower bar u squared plus and a quarter, a half. The Lu L bar u. So this piece violates the null condition. This is L bar direction. L bar is the bad direction. One cannot have a bad direction squared.
So this is simply because when it says nothing to do with the bound, simply because x has to be d bar.
Yes. So if one subtract this part, then it will satisfy the null.
This assumption we don't assume the bad guy.
Yes. Yeah. So there's no bad term. There can be good bad and good, but no bad term. Okay. Now let me state the long-time existence result of Kleinman and Christodoulou. Okay. So for any smooth function with compact support, C, and here I assume Q du satisfies null condition. Then there exists a small number, epsilon 1, depending on Fg and Q. Such that for any epsilon less than epsilon 1, the system with, the equation with small data, box U equals Q du, and U0x equals epsilon f dtu 0x equals epsilon g, has unique smooth solution. In, well, the whole space-time. One can solve it forward, and, well, backward is symmetric. Okay, is there any question about the statement of the theorem?
We know this is actually sharp.
What do you mean sharp?
I mean, well, Q cannot be written in this form. Then you can find the blow-up solution.
There's a lot of other rooms. For example, F can actually depend on U and du as well, but one need to assume on something else. Here I express the simplest form, and
Because your K is only generalizes 7-dimensional vector field.
yes.
We presume that there still is a boost vector field.
So in this nonlinear application, one often don't want to use the boost vector field because it depends on the t, the vector of growth in the t direction. So, Jordan, what? So the Wignall condition is for a system. If you have not only a scalar but a system. Q1, the U here you represent U1, U2, Q2, du. So the Wignall condition says that the null condition says, well, Q1 and Q2 satisfy the null condition. There's no bad term. There's always a good bad. And the Wignall condition says something like, for U1, it can be bad U1 times bad U2. But for U2, it needs to be it needs to satisfy the null condition, the U1, the U. Something like this. For one component, it satisfies the null condition. There's other one doesn't. But it does not satisfy in this sense. This is bad, but one bad term satisfies the null condition. So this is the Wignall condition. Okay, any other questions?
Again, PU2 is really good enough. So it's a little bit weaker.
Let me.
I will assume we should have some kind of component equal plus alpha beta, the sum will should equal 2.
Yes.
Why is it only 1?
Only one is good enough. So let me think. So the problem, if you do the estimate without the null condition, is the crossing will actually feed back. The way one treats this nonlinear problem is to treat the quadratic term as the perturbation. One thing Q, well, if there's nothing here, we know it decays, so it's small. The quadratic term is actually even smaller, so this is a perturbation. But as one really write it, express it, this is actually not the case if you have a bad direction. So that will behaves like f prime equals f squared. It will behave more like this kind of D that always blows up. So one want to avoid this kind of self interaction. But here Q is, well, formally good, and here there's not a self interaction. We have the U2 part, not the DU1, DU1. Yes.
In general, we should consider not just a scale value function plus U. We should have some kind of tensorial plus equation, I guess.
Yes. So.
Only that will do.
So, well, it depends on which kind of question we want to ask. For example, for the linear gravity, one always have a system. But here today, I will focus on the scalar case. So, right. Any other questions? Okay. Of course, I'm not be able to give you the whole proof, but let me tell you some key ingredients. There are two parts. One is the energy estimate. The other is the point-wise estimate. Energy estimate. For any P belongs to 0 to 2, the following is true. Let me define the new EP energy. EPU at time t is defined to be integration over R3, t equals t prime, R plus 1 to the power of p times the LU squared, angular direction. These are the good directions. Their weight is higher, Rp, plus 1 over r squared dr u. So here one can put dlu, but it's just any other direction. Plus 1 over r squared u squared dx. So for any p belongs to 0 and 2, and any out t2, so you say t1 greater or equal to 0, that's EP of u at time t1 is bounded by the initial energy at time 0 plus integration 0 to t integration along r3 r to the p plus 1 box u squared dx dt. So this also follows by a vector field method combining all the vector fields we discussed, but it's integrated along the time slice. So now we are, let me have a picture. We are back to Minkowski. And we work with these time equals constant slices. Okay, so we talk about the vector field method when box u equals 0. If that's not 0, well, we need to carry it all over. And this will be the extra term. This is the EP, and I need another, the boundedness energy, bounded by the initial one, plus 0 to t, r3, r2 squared, yes, box u squared dx dt. This is the energy estimate. And we need the point-wise estimate. So that's for, this holds for any p greater than or equal to 0, r to the p plus 2 times the L infinity norm of d bar u squared is bounded by EP u plus integration r3 rp times box u squared dx. So this is at fixed time slice. And here I need not only EP, but EP3. Here, EP KU is defined to be summation over all multi-indices less or equal to K E of K alpha U. I need to commute with the Killing vectors 3 times to control the L infinity norm of d bar U. And just to convince you that d bar is better, for if we don't throw a bar here, what we have is du, the weight will be only p squared. Will be the same thing. The d bar energy, the d bar decays faster along the r direction. And the last one, r squared times du. This is using the p energy. If we use the bounded energy, then what we have is EP u. Here we also need to commute with Killing vectors 3 times, plus r3 box u squared dx. Okay, so these 3 are the point-wise estimate. So actually, each individually is not hard to prove, but because of time, let me just pick one of it to show you how does the proof go. Let me show you this part for d bar equals L. For d bar equals L, I want to control the L derivative of U. So fix R naught greater or equal to 1, because if R naught is less or equal to 1, this weight doesn't is not important. So again, by Sobolev embedding, U squared at R naught star is bounded by integration along the sphere with radius R naught, commute with Killing vector fields. Here I am going as dl equal to 2 dlu squared dv tilde. And let me focus on the base term when this is, well, not just the L2 norm of gradient Lu, R naught gradient Lu squared dv tilde. The thing is, that's the same trick. Take the derivative and integrate it to the infinity. R naught to infinity. S2 R, then we have twice dr gradient Lu times gradient Lu times dv tilde dr. Use Cauchy-Schwarz and rewrite this volume form in terms of standard one. Integration R greater or equal to R naught 1 over R squared times gradient squared plus 1 over R squared times dr greater dx. The first term is quite easy to deal with. Let me write this as R greater or equal to R naught. Let me put R to the power P. That's the thing appears in the EP energy. Rp. And here we have R to the P plus 2. And R is greater or equal to R naught. I can throw it out. Not P plus 2. And the rest is bounded by the EP energy. So that's the first term. For the second term, we are going to use the wave equation, box U. That's minus dt dl plus dr dl plus 2 over r dr plus summation I goes from 1 to 3. Sorry, here. So here, and what I did was, let me throw in R squared over here, make this part the standard R squared dv tilde. Sorry, I forgot to mention dv tilde. That's the sine theta d theta d phi, the unit volume form for sphere. And convert this to the dx dy dz. I need to throw in R squared and divide R squared and just Cauchy-Schwarz. Sorry. Okay. 1 over R squared omega I squared. This part is angular portion. Write it as the angular killing squared and sum over them. Therefore, move the terms around. dr dlu. That's squared is bounded by box U squared plus dt with Lu squared plus 1 over R squared dr U squared. For the last term, let me write omega that's comparable to gradient slash. So that's 1 over R squared gradient slash omega U squared. And what's the factor we are integrating? That's 1 over R squared. Put in 1 over R squared over here, 1 over R squared. squared becomes 1 over r, which is bounded by, for the first term, I want the power to be rp. So the rest, I have 1 over r to the p plus 2. And for the second term, I can also put weight rp, because I can think it as gradient L acting on dtu. I consider t as a member of K. And for the rest of the term, you can use the similar method. Finally, integrate it, everything. The first gives you r naught, p 1 over r naught, p plus 2, r3, box u squared, rp dx, and the rest give you ep. I need to commute it with killing ones, ep1, u. Okay, so this is the bound for the second term, but that's just the base. I need to commute with killing vector twice, even more. That gives the number 3 over here. And yeah, sorry, here I need to, instead of just u, I need to commute. And I need to do the same thing here. Okay, so these are the main ingredients. And the proof is by a bootstrap argument. Part of it, let epsilon naught to be a very small number to be determined. Let me say KL is 10, KS, that's 7. And the bootstrap assumption is the following. First, I want to assume for any, for some, I can solve the equation for a little bit of time, that's capital T. Any t belongs to T to capital T. The E2 energy, I need to commute it with it 10 times, KL of U is less or equal to epsilon naught. Second, 0 to T, the EP energy, I also commute it with it killing vector fields 10 times. It's T less or equal to epsilon naught. And I need one auxiliary condition, that is for P equals 1 or 2, the integration along R3, RP times box U squared dx is bounded by this some constant C naught times the P energy. I need to commute with 3 times U. And here I also need to commute box K less or equal to Ks. And here that's 3 plus Ks of U. This is the bootstrap assumption, and by making epsilon 1 much less than epsilon naught, we can have at t equals 0 EP KL E2 KL U at time 0 is bounded by epsilon naught squared, and EB KL U is bounded by epsilon naught squared. And this holds with C naught replaced by C naught over 2. Sorry for my ordering. I should first take epsilon naught to be very small such that this satisfies. Then I have a solution for a short time, and I want to look at the time where this estimate is still satisfied. I need some room over here. Then the bootstrap assumption is about, okay, then one can actually improve the bootstrap claim. The claim is there exists a constant, C star, C star, such that one can improve the right-hand side to be, instead of epsilon, one have C star, epsilon naught squared, C star, epsilon naught squared. Instead of C, one have C star times epsilon naught. Then one choose epsilon naught to be very tiny, such that this is less than a half. And this is let me see, yeah, a half. C naught. And one can continue the solution from it. Then one have the long time existence. So the main argument is how to move from this bootstrap assumption to the improved one. The pointwise estimate, I want to keep them. And let me show you how to how to improve the first assumption. One, well, then fix a multi-index alpha. Let's go to KL. Take V to be K alpha U. Then apply the energy estimate to V. So for EP V at time 0, sorry, at time t is less or equal to its initial one plus integration 0 to t, integration along R3, Rp plus 1, box V square dx dt. Now actually p equals 2, but let me write as p, just it will actually make it clearer what we are doing. So the first guy is, well, bounded by epsilon naught squared from the assumption, so it's good. Don't worry about it. So let's look at the second term, especially box. What is box V? Box V, that's box K alpha U. K is Killing vector, commute with the D'Alembert. K alpha, box U, that's K alpha, QU, Q du. And remember, Q du, let me just write systematically as du contract with dBARU, which actually means, I already erased, but actually means there's some coefficient whose derivative along the K is always bounded. So that's summation, alpha 1 plus alpha 2 less or equal to alpha. I want alpha 1 to be the smaller one. Let's go to alpha over 2. There will be two terms, dk alpha 1 u contract with d bar k alpha 2u plus d bar k alpha 1u times d k alpha 2u. Alpha 1, the way is we are going to use the point 1 estimate for the fewer derivative term. And for the rest, we are going to use the energy estimate in the bootstrap assumption. And here I think I missed one term in it. That's actually crucial. Here I need to add the integration 0 to T1 EP minus 1. This is the bulk term you have when doing the energy estimate. You have this bulk term. Okay, because of the time, let me just do it for which one do I want to do? Let me do it for this term. So for d k alpha 1 u d bar, we want to use the L infinity control. Over here, I want to throw in r to the p plus 1 in this, that's 3. Because my m is, I want p minus 1 over here. Bounded by EP. Here I have alpha 1, so that's 3 plus alpha 1 u, and plus integration along R3 Rp minus 1 box k, let me write over here, plus R3 Rp minus 1 box alpha 1, I need to commute 2 times more u dx. So the first term, p equals, here's p minus 1. The bootstrap assumption, the E2 energy is bounded by epsilon naught, so E1 energy is also bounded by epsilon naught. Sorry, I take it back. I don't want to do it there yet. I want to use the third bootstrap assumption to control this term. Here, p equals 2, p minus 1 equals 1. I can put 1 over here. So it's bounded by the E1 energy. So it's bounded by C naught plus 1 times E p minus 1, 3 plus alpha 1. Alpha 1 is less or equal to alpha over 2. Alpha is less or equal to KL. Over 2 U. I don't want to erase this. Let me erase the main theorem. Therefore, Rp plus 1 times this term squared, d bar k alpha 1 u times d k alpha 2 u squared. I throw k r to the p minus 1 over here together with the d bar term and with, sorry, p plus 1. Sorry, I confused myself a little bit. Here I have p plus 1 squared. So p plus 1 with d bar bounded by C naught plus 1 times epsilon naught times E p minus 1. And let me replace this KL over 2 plus 3 by KL. U times d alpha 2 u squared. After integration, this is just a number. Let me copy it. Epsilon naught KL u times, and the integration of this part can be bounded by the EB energy. By the bootstrap assumption, this is less or equal to epsilon. Epsilon squared. Now let me pretend this is the only term occur in on the right hand side. So what we have is EP V times T, EP V times 0, plus C naught plus 1, epsilon squared, E P minus 1, KL U. Then summing all over multi-indices, we have EP KL U bounded by EP KL U. This at time t, this at time 0, and this is the same. A constant depending on KL. C naught plus 1, epsilon naught squared, EP minus 1, KL U. And here I forgot the integration, 0 to t prom, t prom. And this is a place where I need the term I already forgot. KL. So we have this term on the left-hand side, and we have that term on the right-hand side. It's a place to make epsilon naught to be very small to absorb it. Over here, then, well, the EP energy is bounded by the initial one, which is controlled by epsilon naught squared, which is the one we are looking for. Then one do the similar thing for the 2 and 3, improve each one, disclose the bootstrap, then you have the long time existence of the solution. Okay, any question? So let me stop here, and thank you for your attention. Mm-hmm. Yes. Uh-huh. No, but
That's the one that gives this solution. This Young solution. What kind of, I mean, because that kind of semi-linear form is not really invariant form. I mean, you can choose your, you can change your function by a different one.
yes, that's right.
Is there a characterization of this? I mean, just like this example that Jordan pointed out, you can actually transform to the solution, this Young solution, or you can actually transform. I thought that's just a simple transformation. You can make it look like this kind of quadratic blow-up solution. And that's the reason why you argue that always blow up.
Let me think. You mean a more intrinsic way to characterize the null condition? So.
I mean, yeah, I think that's a transformation rule, right? This John solution, you can transform by some. You write it as a function of u or something, and then you can see that in the quadratic blow-up.
Yeah. So so first, here we assume the null condition all the way, but one actually only need to assume it for R large. So that's actually something about the infinity. In the boundary region, one don't need to assume any structure. So one probably need to say fix a coordinate near the infinity so probably that's also related to the coordinate trench near the infinity. Or if you change your lead.
You want to capture, but you want to find a way to describe it in a more invariant way.
Yeah. Greater U squared GU. Yeah, I don't know. Yeah, sorry. So the null condition is to decompose. Here we have the good term, and the bad term. And the good term, we use the, where is it? Yes. In the L infinity estimate, it can have a better weight. So if we throw every weight r to the p plus 1 to the bad term. If that's, sorry, to the good term. I always confuse myself. If that's bad, then the best you can do is just rp times it. Then you are left with a factor of r, then you are left with a factor of r over here, whose integration is not in the bootstrap assumption.
The pattern is always pairs.
Yeah, the good term. Yeah, so for this one, you will throw in some weight for the bad term, use infinity. You have some weight left with the good term, but the good term in the, sorry, I'll always erase it in the good term, rp plus rp d bar u squared. You can throw in a better weight, that's rp. For the bad term, that's r to the p minus 2.
是谁？学生怎么这么清楚？从头都不用看笔记本，你看那是跟谁读？
啊？
跟谁？
我 MIT 是跟那个我的 mentor 是 Minipos， 不过我们不太也没有谈。
哇，怎么这么厉害？
没有，
你是台大哪一年毕业？
我是95年进来，99年。
99年毕业。哇，这怎么都背，真厉害。
没有，今天忘记带 note。
哇，复杂。
开场前20分钟啊，什么？